Myself, Dr. Mallikarjun S. Biradar, Assistant Professor in Mathematics, Government First Grade College, Masuvakalve. Now, the session 8 of Graph Theory 2, we are going to discuss a topic. The title is Hamiltonian Path, Hamiltonian Cycle, and Hamiltonian graph. Okay. Now, Hamiltonian path, Hamiltonian cycle, Hamiltonian graph. In general, first we try to discuss the Hamiltonian graphs. Let me give the introduction about the Hamiltonian graphs. In the beginning, I have given introduction about the Eulerian graph and Hamiltonian graph in brief. Let me recall how we got the Eulerian graph while solving a famous unsolved problem of that time, the Königsberg bridge problem. So Euler, what he did, he has taken the same problem on a paper, so with vertices and edges, and with that concept, the concept of graph come into existence while solving a physical problem, Königsberg bridge problem. Okay, if you concentrate the Königsberg bridge problem, the concentration mainly is on edges, so it must contain all edges and no edge is repeated. Okay, only you have to trace exactly once and no edge is repeated. That was the main concentration in the Königsberg bridge problem, and later on the concept of Eulerian graph is also defined based on that problem. Okay, so Euler gave a solution to the Königsberg bridge problem. With that, so we got the concept of graph in graph theory and how the concept of Eulerian graph is defined. So what is the main concentration in that Eulerian graph? That graph contains all edges of the graph and no edges repeated. That was the main concentration. Okay, in the same fashion. Okay, so to know about Hamiltonian graphs, so Eulerian graph come with the help of or by solving the famous unsolved problem of that time, Königsberg bridge problem. How the concept of Hamiltonian graph come into existence? Let me give some introduction about this. In the year 1857, Sir William Hamilton introduced a game consisting of a solid regular dodecahedron made up of wood. Dodecahedron, I think everyone has saw the football type structure. Okay, dodecahedron, and each face is a pentagon. Of course, there are 12 faces, and if you count the corners, there will be 20 corners, and if you count the edges on each face, so there will be 5 edges, okay, lines. So therefore there will be 12 faces, 20 vertices, and if you count the edges, it will be in terms of 30. So what he did, he has considered a solid regular dodecahedron made up of wood. Okay, so there will be 20 nails he has inserted in each corner of the dodecahedron. What he did, he has inserted 20 nails in each corner of the dodecahedron and supply of a string. He joined the vertices by, that is those the corners, the edges he has joined with the help of a string. Okay, then what one has to do, every corner was given the name of an important city of the time. Okay, the object of the game was to find a route along the edges of the dodecahedron which visits every city exactly once. Every city is nothing but every vertex exactly once, and ends where it began. So you have to start your route from one of the vertices, and you must visit every vertex exactly once, and you must come to the same point where you have started your route or you have started your journey. So there was in the Euclidean graph every edge, here every vertex. That's the difference. Okay. So ultimately, in order for the player to keep the track of the cities visited, the player used the string to join nails in the order in which the route proceeded. Okay. So therefore, the object of the Hamilton's game may be described in graphical terms, namely to determine whether the graph of the dodecahedron, which I am going to draw now, the graph of the dodecahedron has a cycle. It has a cycle containing each of its vertices, containing all vertices or each of its vertices, hence the term Hamiltonian, containing all vertices, hence the term Hamiltonian. So therefore, Hamiltonian's game asks the player to find a cycle containing every vertex in the graph of the dodecahedron. Okay, so this is how the concept of Hamiltonian graph come into existence while playing a game with the dodecahedron. So therefore, let me draw the dodecahedron first. Okay. Okay, I try to draw the dodecahedron. Okay. Let me try to draw the dodecahedron first. As I said, there are 12 faces. Of course, one face is not visible here because it's a two-dimensional one. Then, okay, I think, okay. Just I think I have made a small mistake. Of course, doesn't matter, but there is a small mistake. Let me redraw the inner part of the graph. Okay. Instead of taking here, I shall take here. Okay. This would be better. Okay. Now I join. Yes. Now this is the graph of the dodecahedron. Okay. If you see every face, it is like a pentagon. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So these are the points where he has inserted the nail and joined with the string like this. Okay. So ultimately we got a dodecahedron. So this is the graph of a dodecahedron. One has to start a route. So he has given the name to each and every vertex. Every vertex is given a name of the city. So he has to start from one place, okay, one city. He has to visit every city exactly once, every city exactly once, and come back to the same vertex where he has started his journey. So that's the difference between the Eulerian and Hamiltonian. There, every edge exactly once. Here, every vertex exactly once. So this is how the concept of Hamiltonian graph come into existence while playing with the dodecahedron. Okay. So this is the graph of the dodecahedron. If you want, you can try. Of course, like this. Our interest is to consider the vertex. So like this. Okay. Then like this, then like this, okay. Yeah, yes. So this is how There is a cycle containing every vertex of the graph. There is a cycle containing every vertex of the graph. There are 20 vertices like this, like this. I have redrawn like this. Okay. There is a cycle containing every city or every vertex of the graph. Okay. So if such a cycle is there, then you can say there is a concept called Hamiltonian cycle or Hamiltonian graph. So that we will see in detail. Okay. I hope you have followed. So the Eulerian graph from the Königsberg bridge problem, the Hamiltonian graph from the dodecahedron. Okay. Now first we try to define Hamiltonian path. What is Hamiltonian path? Hamiltonian path. Already in the previous class we have discussed walk, we have discussed the trail, we have discussed path and cycle. Okay. So Hamiltonian path, a spanning path in a graph is called a Hamiltonian path. Spanning graph, spanning subgraph. Spanning, whenever we use the word spanning, it implies it must contain all vertices of the graph. Okay, you must consider all vertices of the graph. So there should be a path containing all vertices of the graph is called a spanning path. A path containing all vertices of the graph is called a spanning path. So that path is called a Hamiltonian path. Okay, so let me consider one example. Okay, so this is one graph. Is there a Hamiltonian path? What I say, Hamiltonian path is a path. It is a path. What kind of path it is? It is a spanning path. A path containing all vertices of the graph. Let me label the vertices as V1, V2, V3, V4. So there is a path from V1 to V2, V2 to V3, V3 to V4. So this is the path. So you may say that, sir, you have not considered this edge. So here importance of edge is not there. Importance of edge was in the Eulerian graph. Here importance of every vertex in the Hamiltonian graph. Okay. So it is a path. There is a path in this graph containing every vertex of the graph G. So such a path is called a spanning path. And that spanning path, if it exists, that path is called a Hamiltonian path. So therefore, this graph has a Hamiltonian path containing V1, V2, V3, V4. So such a path is called Hamiltonian path of the graph G. I hope you have followed very easily. Okay. Next, consider Hamiltonian cycle. Hamiltonian cycle, simple cycle, a closed path is called a cycle. What we defined in the previous classes in the previous semester. A closed path is called a cycle, an ordinary cycle. Okay. So now what is Hamiltonian cycle? A spanning cycle or a cycle containing all vertices of the graph is called a Hamiltonian cycle. For example, if I redraw another diagram, okay, let me draw here only. Suppose I may take one more vertex, say V5, I rejoin like this. Okay, doesn't matter. This is another graph. This is another graph. Whether there exists a cycle containing, cycle is nothing but closed path containing all vertices of the graph. If it is so, then that cycle is called Hamiltonian cycle. So we start with V1, then V2, next V3, V4, V5. Yes, there is a closed path which is called a cycle containing all vertices. All vertices. We have started at V1, V1 to V2, V3, V4, V5, V1. No need to consider the edges, but there is a cycle containing all vertices. It is called a spanning cycle. A spanning cycle. Spanning is nothing but containing all vertices of the graph. So such a spanning cycle is called Hamiltonian cycle. So therefore this graph has a Hamiltonian cycle. So what is the cycle? This is the cycle. So V1, V2, V3, V4, V5. So this graph has a Hamiltonian cycle, or you can say a spanning cycle containing all vertices of the graph. So such a spanning cycle is called Hamiltonian cycle. Okay. Next, what is Hamiltonian graph? Next one is Hamiltonian graph. A graph containing Hamiltonian cycle is called a Hamiltonian graph. A graph which contains Hamiltonian cycle is called a Hamiltonian graph. This is an example of a Hamiltonian graph because this graph contains a Hamiltonian cycle, or you can say a spanning cycle which is called a Hamiltonian cycle. So this graph has got a Hamiltonian cycle or spanning cycle. So that's why this graph is called a Hamiltonian graph. I hope you have followed this very easily. So because the importance in this graph is it must contain every vertex. No vertex is repeated. You see, this is a closed path. Closed path. Closed path is nothing but only starting point and ending point are coincident. They are unique. But apart from the starting and ending, all our vertices are distinct vertices. There is no repetition of vertex. As in the case of Eulerian, it must contain all edges and there should not be any repetition of edges. In case of Hamiltonian, it must contain all vertices and there is no repetition of vertex except the first, where we have started. Okay, right? But starting and ending are different. It is called Hamiltonian path. If starting and ending are same, it is called Hamiltonian cycle. Any graph which contains a Hamiltonian cycle is called a Hamiltonian graph. I think you have followed the concept of Hamiltonian path, Hamiltonian cycle, and any graph which contains a Hamiltonian cycle is called a Hamiltonian graph. So this is another important concept. Okay, so as we have discussed about Eulerian, and this is another important concept called Hamiltonian graph. And Hamiltonian graph, if you observe properly, Hamiltonian graph, again it is a connected graph. As Eulerian graph is also connected, similarly Hamiltonian graph is also connected because it contains a cycle. When it contains a cycle, obviously it is a connected graph. So this is one observation. Okay, so in the next class we consider some examples based on Hamiltonian path, Hamiltonian cycle and Hamiltonian graph. Similarly, we consider some characterizations. See, it's very difficult to say the characterization. We have got characterizations for Eulerian graph. A graph is said to be Eulerian if and only if the degree of every vertex is even. Or a graph is Eulerian if and only if it is possible to partition the edges into cycles. Like that, whether we have got the general results, the characterizations for the Eulerian graph. So that we are going to discuss in the next class. So first we discuss some other examples on these concepts. Then we consider the results, whether the results are, whether any result, general result is there or not, or whether any other necessary and sufficient conditions. That all we discuss in the coming classes. With this we conclude. Thank you.